Here is an illustration of how we test split brain patients. A split brain patient has had their corpus callosum cut surgically. This is done in extremely rare cases of epilepsy to save a person's life. The corpus callosum connects the left and right hemispheres of the cerebrum, the top wrinkly part of the brain. So this person on the left, in the illustration, this woman, has had split brain surgery. So her left hemisphere and right hemisphere are disconnected from one another. Now, on the right, we have a psychologist. You can tell it's a psychologist because he's very handsome. The psychologist projects an image on the screen. For example, here we have an image of a spoon projected to the patient's left field of vision. So we have the split brain patient staring straight ahead at a dot in the middle of the screen, and on the left is the image of the spoon. Well, images on the left, whatever we see on our left field of vision, is seen by the right hemisphere because of the wiring from the eyes. So both eyes send this information to the right hemisphere. So her right hemisphere sees the spoon. Now, if the psychologist asks her this question, what do you see? Both her hemispheres will hear the question. But the left hemisphere is in charge of language and in charge of speaking. The left hemisphere sees things on the right, which is nothing. So this girl's left hemisphere says, I see nothing. Now the psychologist says, reach under the screen with your left hand. Now both hemispheres hear that statement, and the right hemisphere is in charge of the left hand. So the left hand reaches under, controlled by the right hemisphere, and grabs the spoon. Because the right hemisphere has seen a picture of the spoon, it knows about the spoon, but it's not in charge of talking. If we then ask the person, what are you holding in your left hand? She says, I don't know. That's the left hemisphere that doesn't know. The right hemisphere knows, but it's not in charge of talking. This man has had his corpus callosum cut, so he has no connections between his left hemisphere and his right hemisphere. We sit him down in front of a screen, he stares straight ahead. We put the word ball on the left side of the screen, which is seen in the right hemisphere through both eyes. Because it's on the left, it stimulates cells on the right side of each eye, and the right side of each eye is connected to the right hemisphere. And so his right hemisphere can see the word ball, and therefore his left hand can find the ball. But when we ask him what he sees, when we're using language, when he wants to speak to us, he's using his left hemisphere. And his left hemisphere sees things on the right, and there's nothing on the screen on the right, so his left hemisphere sees nothing, and it says, I don't see anything. Here's a very similar example. Split brain patient looks straight ahead at the dot on the screen. On the left side of the screen is the word key. If we ask her what she sees, what will she say? Well, left hemispheres speak. The left hemispheres see things on the right. So the left hemisphere sees nothing, and she'll say, I don't see anything. But her right hemisphere sees things on the left, sees the word key. Can her left hand find the key? Yes, because her left hand is controlled by her right hemisphere. Remember, she has a cut corpus callosum. If it was you, of course, your two hemispheres can communicate because you have a corpus callosum. But this person has had the wires cut between their left and right hemispheres. In this example, a split brain patient stares right at the middle of a screen. On the left of the screen is the word key. That means his right hemisphere sees the word key. Because his corpus callosum has been cut, his right hemisphere cannot send the signal over to the left hemisphere to tell it about the word key. So the word key is only seen in the right hemisphere, which controls the left hand. The word ring is on the right side of the screen. things on the right are seen in the left. So his left hemisphere sees the word ring. If you ask him to say what he sees, he says ring because that's his left hemisphere talking. His right hemisphere can show you what it sees using the left hand, so the left hand can find the key. By the way, if you ask him, what are you holding in your left hand? He says, I don't know, because he can't see it with his left hemisphere. That is, if he moved his left hand over to the right side of his visual field, then his left hemisphere would see it. You've been working hard on these slides. Time for a cartoon break, and then we'll go on. Here are two more examples of this weird thing that happens when we test split brain patients, people who have had their corpus callosum cut. Remember, you can go on YouTube. You can watch, for example, a video called Severed Corpus Callosum, and you will see a man who has split brains, who's had split brain surgery, and does some of these experiments. All right, on the left here, a man staring straight ahead at the screen, and there's an orange in the right field of his visual field, and so it's seen by his left hemisphere, so he says, I see an orange. The man on the right says, I see nothing, because his left hemisphere sees things on the right, and on the right there's nothing. But on the left field of vision is an apple, which his right hemisphere sees, so his left hand can find the apple. Here's an illustration I found online that shows how the split brain phenomenon works. So images on the left field of vision are seen in the right hemisphere, which doesn't speak, but controls the left hand. Images on the right field of vision are seen in the left hemisphere, which can speak. Well, here's an interesting experiment. We show this face, which is made of vegetables, to a split brain patient. And the question is, well, will the split brain patient say it's a face, or will they say it's vegetables? Or will they say it's a face with vegetables, which is what we would say? And it turns out it depends on which hemisphere sees it. When the left hemisphere sees it, the left hemisphere says that's a bunch of vegetables. But when the right hemisphere sees it, the right hemisphere says, I see a face. Well, the right hemisphere actually doesn't talk. We have the person point to words, and the person will point to the word face. So how do you show this to the left hemisphere and the right hemisphere? Well, you put it on one side or the other of a screen. If it's on the right side of a screen, then the person's left hemisphere will see it and will say, that's a bunch of vegetables. But if you put this face on the left side of the screen, so only the right hemisphere sees it. This is a split brain patient. No connections between left and right hemispheres. So you put the face on the left side of a screen. So only the person's right hemisphere sees it. They will point to the word face. What does this tell us? It tells us that right hemispheres are really good at putting things together into a pattern. Right hemispheres are good at like maps, at understanding patterns, whole patterns. Left hemispheres are good at analysis, analyzing, breaking things down into their bits and pieces, finding the details, looking for the little bits and pieces, the details of something. So left hemispheres better at analyzing things. Right hemispheres better at synthesizing, at putting things together into a package, a pattern. Here's the slide I made to help you remember some of these lateralization differences between left and right brain hemisphere. Left hemisphere tends to be better at logic and analysis and language and details, analyzing something, breaking it down into its bits. Right hemispheres tend to be a little bit better at global tasks, at holistic concepts, at maps and patterns and faces, for example. Maybe the differences aren't great, but they are there. The left hemisphere seems to be specialized for certain things, right hemisphere specialized for other things. Well, we finally worked our way up to the most interesting slide. Now that you know something about lateralization, I think you'll be very fascinated with this experiment. The experimenter's name, Michael Gazzaniga. If you look on YouTube at the video called Severed Corpus Callosum, you'll see Michael Gazzaniga. He is not the first person to study split brain. The first person was Roger Sperry, a psychologist who won the Nobel Prize for his studies of split brain patients. So he's the one who discovered this lateralized difference between left and right hemispheres. Anyway, Roger Sperry had a student named Michael Gazzaniga, who now studies split brain patients as well as many other things. So Michael Gazzaniga did this experiment some years ago where he had a split brain patient sit down in front of a screen, and he put a snowy scene on the left and a chicken's claw on the right, just as I've illustrated here. Then he took those pictures away, and he showed the split brain patient a series of pictures to choose from, and asked the split brain patient to point at an object that was related to what they had seen on the big screen. And the split brain patient with the left hand pointed at a shovel, and with the right hand pointed at the head of a chicken. Now we know why the split brain patient is doing that. The snowy scene was on the left side of the field of vision, the visual field, the left visual field, therefore seen by the right hemisphere. And the right hemisphere controls the left hand. So the left hand pointed at a shovel. That goes with the snowy scene. The chicken's claw was on the right side of the screen, which is seen by the left hemisphere. The left hemisphere controls the right hand. So the right hand pointed at the head of a chicken. What was interesting was that Gazzaniga then asked the person, why are you pointing at those two things? Okay, when you ask this question, both hemispheres hear the question, but only the left hemisphere is in charge of language. So the left hemisphere is going to answer, but the left hemisphere only saw the chicken's claw. So it's like you only saw a chicken's claw, but now you find yourself pointing at the head of a chicken and a shovel. Why the shovel? Okay, so what did the person say? So Gazzaniga said, why are you pointing at those two things? And she said, I'm pointing at the head of a chicken because I saw a chicken's claw, and I'm pointing at the shovel because you use a shovel to clean out the chicken shed. Her left brain made up an answer that seemed reasonable. Now that's interesting. She didn't say, I don't know. I mean, her left hemisphere didn't say, I don't know why I'm pointing at a shovel. It made up a reason. So this is what we've discovered through lots of other research. This was just the first study of this, what is called confabulation. People make up reasons for why they do what they do. A lot of times we do stuff, we don't know why we're doing it, but our left hemisphere is really good at making up a reason. And it's not lying. I shouldn't even call it making it up, because the person believes it. She really believes that's why she's pointing at the shovel. We know why she's pointing at the shovel. We know because we know that her right hemisphere saw the snowy scene, but her left hemisphere doesn't know that. Her left hemisphere doesn't know what her right hemisphere saw. So her left hemisphere makes up a reason for it. People do this all the time. We make up reasons. We think they're true. We think they're the real reasons. Often they're not. Our reasons are not the same thing as the causes. This is fascinating because what it means is we can't go around asking people why they did stuff. We have to do scientific research to find out why people do stuff. There's one group of people who confabulates all the time that we'll study way, way later in this course. And that is people who have abused alcohol and they have damaged their brain. And they're constantly making up stories that they think are true. This is called confabulation. They're confabulating. They're not lying because they really think it's the story they're telling is true. This is interesting. It's called confabulation. And this is the end of our slides for voice 1 brain. Now you move on to voice 2 brain.